Sweet. Let me just double check that YouTube's working. We should be live. All right, we're live. All right, welcome everyone to another episode of GPU Mode. Today I'm really thrilled to have like a returning guest speaker, Ali Hassani, who's going to be talking to us about like neighborhood attention, sparse attention, and a bunch of like interesting new things to do on the newer hardware. So yeah, Ali, please, without further ado, take it from here.
Thank you. Thank you so much. I'm happy to be back and to talk about this project specifically because this has been my main project for my PhD. So I've been working on this since I want to say late 2021. So it's been going on for a really long time. So I'm really excited to share some of the things that I've learned and specifically some of the things that we accomplished over the last few months. So I'm going to be talking about neighborhood attention, which is a form of sparse attention, but I'll try to introduce it without giving away without focusing too much on the definition and applications and more on the implementation side of things, since this is GPU mode. But I have a bunch of links in the end, references for papers you can read on just the theory of these types of attention patterns, also the papers that we did and the milestones that we went through, and finally I might talk fast. I typically do. So if you want to ask questions, feel free to stop me and just ask questions. And then once I'm done with the slides, we'll go over the code a little bit. I'll go over a live demo on Blackwell. So first of all, why do we care about sparse attention? Why even study this problem? Well, attention is at the core of most foundation models. So that's reason number one. We want to be efficient, and an attention is sometimes criticized for its quadratic complexity, and that's something that kind of also leads to certain workloads being predominantly attention bound. So in image and video and world foundation models specifically, the larger your resolution, the longer your video, or at some point, the number of tokens that you have grows so much that more than 50%, you spent more than 50% of your end-to-end inference time easily on self-attention. So it's really important to, if you really want big returns, it makes sense to go after the bigger piece of the pie. So first, I'm going to talk about what attention does, which almost everybody here is already probably familiar with, but specifically how I define it and how I use the same definition to define what neighborhood attention is. So we know attention is an operation over two sets of tokens, a query and context set. And tokens, well, depending on what your application is, might correspond to different things. And in language, they correspond to words or subwords. And vision, it can be pixels or patches of pixels. But anyway, queries attend to some context to accumulate information. But specifically, I'm interested in self-attention. That's what we call out that has a quadratic complexity, and it's the thing that can potentially limit us as we grow the number of tokens that we have. And use cases for this are the prefill stage in language models and the denoising bit in denoising diffusion models. So usually 90% of diffusion workloads or higher, if you really optimize things, it should be like 98 or 99% or more, is spent on the diffusion itself, because it's an iterative process done over many steps. So naturally it grows to be the biggest piece of your workload, and attention, self-attention specifically, is the biggest part of that workload. But so when we conceptually try to think about what attention does, you can visualize attention, at least the way I'm doing here, mostly on a per query basis. At least I find it useful when I try to build up to what neighborhood attention is. So over here, we're kind of visualizing that no matter where the query is, it attends to the entire context, which is the entire input. So in self-attention, query and context sets are the same thing. We just have different projections of them. Query gets just projected into the attention input, context gets projected into your KV. So this is, and I specifically chose this example because it's two-dimensional, and that's where the problem of doing something like what neighborhood attention does gets a little bit challenging. So over here, we don't have a sequence of 18 times 18 tokens. At least we don't think of it that way. We look at it at a multi-dimensional view or layout of our tokens, which is 18 by 18. And regardless of where the query token is, it attends to the whole thing. Now, what if I want to localize this? I want to introduce sparsity at the dot product level. I want to reduce the number of dot products I do. I want to reduce that ON squared complexity. So if I want to localize it, if I want to use spatial locality to achieve this, I can think of it as self-attention is some form of local attention, but one where your local window size is just 18 by 18. It's just the whole thing. So let's try and slowly reduce that. And we want to try and do that while we try and keep the query perfectly centered within that window. Of course, it's not always possible because there might not be a center because your window is evenly sized, or in this case, the query's a little bit closer to the corner, so it's impossible to get it to be like perfectly centered unless you're willing to just get your sliding window or window just go out of bounds and then attend to nothing. But we don't really want that. We want to attend to as many things as possible. So 17 by 17 kind of looks like this. And this is just how neighborhood attention defines it. And it's a slight shift from how previous instances of multidimensional sliding window attention, particularly in 2D, looked like. So if we keep going, we can slowly keep reducing this. And as we do this, we're moving away from what is self-attention. And we're just kind of in new territory. So this is not self-attention. It is just neighborhood attention where, we localize attention, and we can keep going. There's not really anything limiting you from changing these numbers whichever way you please, as long as they're greater than or equal to 1, and as long as they don't exceed the bounds of your problem. So you can kind of keep doing this, and you can even set it to 1. But a 1-by-1 context window is just a linear projection. So now you have 0 attention. It's just no longer attention. It's just a linear projection. And the reason for that is if you have a single dot product per query, the softmax of a single element is just always 1. So you're just accumulating the value corresponding to itself. So you might as well just not do attention, throw out QK, not compute it at all, and just use V. So this is something that I usually bring up in these sorts of talks because it's one of the things that I like about neighborhood attention is that it allows you to do this. Like, it allows you to bridge 2 operations that we use everywhere in most modern neural networks, at least most transformers anyway. And those 2 are attention and linear projection. And it kind of bridges, it kind of builds a bridge between them. So you can have something that's neither one of the 2, but like closer to attention. So that's basically exactly what neighborhood attention does, is that for each query, it localizes the attention window, the context window, whatever you want to call it, to a local window around it. And you, as the end user who would get to put this in, I don't know, some neural network architecture, you get to decide what that window size is. And well, the smaller it is, the less work you are technically doing, but actually saving you compute is going to be challenging, but I'll talk about that in a few slides. So the problem with this was when we first had this idea back in 2021, late 2021, we just had to write our own CUDA kernels from scratch. I was just a new PhD student, so not a lot of context into, okay, do I use Triton? Do I use Cutlass? Or I wasn't even in that mind space. I was like, all right, we need to go at least one level below PyTorch to be able to accomplish this and still get the savings that we expect to get. You could have implemented this just with attention mass, but the whole point was, well, how do we save memory? Before flash attention, one of the big things you really wanted to do whenever you tried to work on something that's a sparse form of attention is actually save memory. And if you fully materialize the attention weights and just use an explicit mass, you're not going to see those savings, not in memory nor in compute. But the bigger problem, which we later came to realize, was this is no longer a matrix multiplication problem, and attention is comprised of 2 big matrix multiplies. And the reason why this is not convenient is that if you want to accelerate attention, ideally you want to keep it still dense computation, but if you go to something that is not really dense, that is more a vector matrix multiply, then you're not really highly utilizing specialized hardware, and most hardware accelerators for AI keep on getting better and better at dense linear algebra. You want to have enough work to do to keep your utilization up, and switching something that's already a matrix multiply that can utilize your resources pretty well to a vector matrix multiply would suffer many challenges. So
I'm sorry, Elise, just since you did say it's okay that I slow you down, like, At least like when I look at this visualization, it kind of looks like a convolution, which is a
Yeah,
matrix
exactly.
multiply. So where does the vector part come in here? Like, what's the vector
So
exactly?
so yeah, so your query, this one query is one vector, but the context that it has. So the reason why it's a vector matrix multiplication technically is that the query right next to it, if you move by one, the window shifts, right? So you have one vector that's your query, but your context, your KV, changes depending on where the query is. So if you want to implement this, the most straightforward way to implement this is with a vector matrix multiply. But then, as we'll see later, you can kind of compute this as a matrix multiply as long as you have
Oh,
masking.
so it's a vector of three elements, basically the three channels of the matrix, right?
Well, yeah. Well, here we don't introduce channels, but yeah, whatever number of dimensions your attention would have, whatever your attention like head dim
Oh,
would
your
be the
head dim, I
number of
see.
yeah. So this is kind of just to illustrate that. Suppose this is a feature map. So yeah. But yeah, that would be the vector matrix multiply. You have to multiply query vector by local window, which you can pack into a matrix, and then you have to take the softmax of that and then multiply by the corresponding values, and then you have your output. So that's why it's a vector matrix multiply.
Okay, got it. Thank you.
Great, thank you. But so a bigger problem with this, like even before we decide whether this is going to be fast or slow or what performance it's going to have, is what about global context? Like one of the big points of using attention is that you can see everything. You can have global interdependency modeling, and you give some of that away by localizing, and the more you localize, the more that you give away. Well, at the time when we were slightly more application focused, our solution to this was, well, we brought over sliding windows. Why not dilation from convolution? And this actually works pretty well. So we defined the dilated form of neighborhood attention. And this actually has a pretty good advantage compared to convolution, is that in convolution, it's a lot harder to do really large dilations without increasing your memory footprint. If you're doing a convolution with a same padding, which is pretty typical in today's neural network architectures, so if you want to do something that doesn't downsample your feature map, you always have to pad by something that is proportional to kernel size times dilation. So the bigger your dilation or the bigger your window size, the more you have to pad. But with neighborhood attention, you don't have this problem, because, and this goes down to, this boils down to just how attention and convolution are different things. With convolution, you can implement the same idea, but what you would get would be repeated pixels in your feature map or repeated vectors in your feature map. We discussed this in detail in that DINAT paper a little bit, which is referenced in the end. So if you're interested in why this wouldn't be applicable to convolution in the same way, you can look at that paper. But so yeah, our entire goal at that time when we did that paper was, okay, let's suppose we can train models with this, and we did train models with this with whatever implementation we had back then. But then we realized that, okay, we're giving up a lot of this global context. How do we improve performance? And so we found that when you take a VIT, because at the time the focus was hierarchical vision transformers, things like Swin transformer. So those were already dealing with local attention. So of course, compared to those, this would give you superior performance. But we also took VITs and just localize their self-attention to neighborhood attention, not for any performance gains because it wouldn't be much at that scale. And then you would see a drop in like ImageNet accuracy. But then when you introduce dilation, like every other layer, and you mix dilated and non-dilated forms of it, you actually get a pretty decent boost. You get closer to self-attention level performance. So this is like one way that you can deal with it. And in a lot of follow-up research that we've done, which I'll also drop links to, there's like a lot of evidence that using a combination of dilated and local neighborhood attention is actually almost always a better choice. Both if you care about speed and if you care about accuracy, it's almost always a good decision. So the advantage of this form of neighborhood attention is that as long as you don't change your window size compared to the localized one, the cost is the same. The flops are the same. In practice, this actually is usually even faster. And I'll be happy to clarify why, but I won't get into. Sorry, was there a question?
Yeah, so you might be answering this later, but like I'm just sort of is the spoiler that the dilation typically needs to be like within a 2:4 sparse ratio to be fast on modern hardware, or is this like underrated?
No, not well. No. So the point is, so originally we didn't implement dilation this way, but since a year ago we've been implementing it this way, where so dilation is basically standard neighborhood attention on top of a partitioning of your input. So we just pre-partition our inputs according to whatever dilation factor it is, and then we move the additional dimensions to batch. So you get a smaller neighborhood attention problem, but with a larger batch. So just the level of parallelism goes up. So this ends up being the reason why it can be faster, because the more you do dilation, the more likely it is that, I don't know, it is actually possible to so for instance, if your input size is evenly divisible by both dilation and window size, then dilated neighborhood attention is just that partitioning plus self-attention. So over there, you still end up being a little bit faster because you can skip the attention masking as well. So lots of reasons why it ends up being a lot faster, but also there are some limitations to it. But typically, like, doing dilation is either going to deliver you similar performance or better in most of our current implementations.
And which paper do you discuss this, like partitioning, like this idea, this algebra?
So the partitioning was in last year's faster neighborhood attention paper. I'll discuss that in a few slides, and also there's also a link there, but not in too much detail today. If you look at Natin, it's like pretty clear that we do this, because today the way we also design our kernels has changed. So it's pretty like clear today how like dilation is handled. But yeah, the original, like the time that we figured it out and worked it into the implementation was last year's FNA paper.
Mhm.
So any other questions?
No, that's it.
Okay, great, fantastic. So so this gives you, like I said, this gives you some sparse global context, but with the same cost. But so now I want to talk a little bit about implementation, because there was an approach that people had already been using before we started working on this, and that was block detention. So this was like the de facto standard way of doing local attention in Vision, specifically starting 2021, made popular by the famous Swin transformer paper. And so this is really easy to implement in PyTorch, because all you have to do is partition your inputs, again, similar to how we do dilation partitioning, but over here you're doing a contiguous partition versus dilation, which would be kind of like interlaced. I might be misusing these words a little bit, but I think the idea is clear. Like over here, we're just taking contiguous elements and putting them into a partition, whereas in dilation, you skip a few elements. But anyway, so block detention is really interesting, because all you really do is cut up your inputs into chunks, into blocks, and then you do a self-attention on top of each one, which can be done very easily in parallel. And the reason why, one of the things that's so great about this is that you don't necessarily always need to modify your attention implementation. You don't need to change anything at the kernel level to implement this, which is why it was so popular. And also another advantage is you're still doing dense matrix multiplies on each one of these blocks. But then the potential problem with this is that you lose translational equivariance. Or depending on what the block size is, you either relax it or break it. Like the more fine-grained and the smaller your block size is, the harder it is to tell the difference. But so this can lead to inferior performance compared to sliding window or neighborhood attention. And we both found this empirically in some of our work, and has been shown in some other follow-up works where they specifically experiment with blocked versus neighborhood attention. And it's like how much better the quality is highly application specific, how much training data you have, on what scale you're doing the training. But some tasks are very sensitive to this, and for that I could name out. There's this startup in the Bay Area called Windborne, and they're actually developing a model, like a weather prediction model, where they're dealing with huge problem sizes, and they need it like a multi-dimensional type of sparse and local attention. And one of the applications where they did find this to be true, that block detention was simply inferior to neighborhood attention for them, was one of their models. And I'll actually include a link to their blog post, because it's very interesting at the end of these slides when I share them. But anyway, I'm going to move on to implementation. So again, it's no secret that pre-2022, most attention implementations were with just simple batch matrix multiplies. And since then, fused kernels like flash attention have become the standard. So then the question is, how do we introduce sparsity into these fused kernels? And so it's pretty much almost any method that introduces sparsity at the dot product level, meaning you're just skipping computing certain attention weights, and that's where you get your sparsity. If you're doing something like that, then you're most likely going to use block sparsity, a technique called block sparsity, to introduce this into your fused attention kernel. And the way it works is similar in both the forward and backward pass kernels, except the problems transpose and some other details. But so in the forward pass, if we just want to consider the simple case, the forward pass of a fused attention kernel, you tile your query because you load in one query tile and you produce one output tile corresponding to that query input tile. So that's going to be your outer loop, and that's where you get your parallelism. And your inner loop is usually done on the same processor, on the same chip, on the same SM. And so you have an explicit inner for loop in your kernel that goes over these tiles. You might have a scheduling unit, doesn't really matter. But the whole point is, if by the time that you're loading in your Q tile, you can predict which one of these tiles you're going to visit or going to need to visit and which one's not, you can skip the ones that you're not going to visit. And by visiting, I simply mean if I mask out an entire tile, like here, and I don't have a single dot product in it that I'm going to use that my attention mask is just going to get rid of, then there's no point in loading in the K or the V and doing the dot products. So I might as well just completely skip those iterations. And this is basically how block sparsity works. And this is also the reason why, in especially our most recent works and papers, I specifically avoid using flops as an efficiency metric, especially when you're comparing multiple different sparse methods that all apply sparsity to attention via block sparsity, because flops don't really tell you anything. Flops, your savings are never in terms of flops. You either skip a tile or visit it. And if you even need a single dot product in that tile, you're going to have to pay the cost for all of the flops. And so the advantage of blocked attention and why it doesn't need some modifications at the kernel level to accomplish this is that if we think about what it does, like I said, it's a partitioning. And then if we just look at these partitions and we kind of align them this way, you can kind of see that the block sparse mask, if we consider like the block sizes match the tile size in your attention kernel, you can kind of see that the block sparse mask is only lighting up on the main diagonal. So whenever that's the case, you simply don't need to really modify the kernel as long as, because again, like if you're just interested in this main diagonal, you can kind of, when you don't need these interactions, you can move whatever dimension is representing these four tiles into the batch, and then you're just compiling these four on top of each other. I don't know if that explanation made sense, but this is the reason I bring this up is that this is why anything beyond blocked attention is going to need some modification at the kernel level. So for instance, if I wanted my mask to be able to compute these values as well, like these tiles, visit these tiles as well, I really need to modify my attention kernel. It's no longer really so easy, like just to transform this problem into a parallel attention problem and then not need to do anything at the kernel level. So now I'm going to talk about how do we fuse sliding window attention methods like neighborhood attention. And the only additional element is that in addition to block sparsity, you're going to also need to
actually, before you keep going, there's sort of like a few related questions in chat, like which are, so in some sense, like this, like all the neighborhood attention techniques are basically like somewhat like directly competing with techniques like flash attention, and that it's like a different like methodology to reduce like the amount of memory you're materializing, right? I know you're making a face, but just let me finish the question. And so like, so one aspect of the question is like, well, how do you do head to head? And then the other side of the question is, can you reformulate basically all these attention variants you're describing and essentially like pre-process your inputs such that you could just call flash attention and have things like really fast?
So the first thing that you said, I might have misunderstood, but I don't think this as an optimization that would be like competing with flash attention. These are all different forms of sparsity, and what I'm so on an abstract level, as long as there aren't too many, so basically what I'm talking about here are changes that you would need to make to just a pure FMHA or flash attention kernel that doesn't have any sparsity support built into it yet. These are the modifications that you're going to need to make to add sparsity support to it. So yes, to your point, as long as support for all of these unique things that you need to be doing is included in those kernels, then yeah, you don't really need much else. But then that's kind of the problem, is that there's many very specific things that you need to do, which I'll explain a little bit further when you step into multi-dimensional domains. So basically what I'm trying to say is that if you already have, there's already at least some iterations of flash attention that I remember that had sliding window support. Those are all in 1D. And if you want to do 2D sliding windows, it's not going to be so simple. And those are exactly the slides that I have next. So I don't know. Does that answer both questions? I don't remember what the
It
first
does,
one was.
yes.
Okay.
It does actually, yeah. This
Okay.
helps. Thank you.
Great. So any other questions?
No,
great.
yeah, that was good.
Okay, great. So yeah, so the way you go ahead and implement this into a fused attention kernel is by having just both of those components. Block sparsity, figure out which blocks you're going to need to visit, skip the ones that you don't, and fine grained mask. Once you visit each block that you know to be, not fully dense, if there are elements that are masked in it, you're just going to have to traverse through all of those elements, find them, and mask the ones that will be masked off, so that you don't accumulate additional values and numerically match the original sparsity pattern. And so this is actually pretty simple and easy to do. And the first successful example of it was Mistral 7B a while back. And if memory serves me right, the Mistral team contributed both of these features that I mentioned, block sparsity and fine-grained mask, into both Flash Attention 2, which was state-of-the-art at the time, and the Xformers FMHA kernel. So, and since then, I believe it's kind of caught on, and it's in most packages, you can either find it or it's super easy to implement. And there's also been other success stories of just localization working in large language models like Cohere's Command A and DeepSeek's native sparse attention, although that one uses sliding window as one of the methods they use. Llama 4 was based on blocked attention, so I don't believe... Actually, I don't know. I never got to find out. Like, I think maybe it was implemented with flex attention, or maybe that was just the inference. So I'm not going to guess, but these are all, to me, successful instances of block sparse attention, or some form of attention that is block sparse, that you implement with block sparsity in the language space. But the thing that all of these share is that they still live in that single dimensional token space of language models, meaning you only have query sequence length, KV sequence length, everything's an integer, everybody's happy. But then when you step into multiple dimensions, it's going to change. So this is this example that we just saw in 1D. I'm also including something here, which is to say, okay, over here, so the specs of the problem is this. So we have 64 tokens with a window size 16. And so this is like a quarter, right? So you would expect a 4x speed up if you were to go just by flops, right? But if you actually go ahead and count the number of tiles that you end up saving, then you'll see that the upper bound performance, as long as like your Q tile is 8 and KV tile is 4, these are very dummy examples. If you go and calculate your speed up based on just savings in tiles, you'll see that it's actually 3x. So this is like one key inefficiency, you can think of it, in sliding windows, is that this will always happen. This is unavoidable. You will never really hit that flop-wise speed up. So unless you absolutely care about those inductive biases that sliding window gives you, you might not really care about it. And you might go for something like blocked attention. But then again, it would be good if there was a trade-off between those two. So here's what I mean by it gets complicated in 2D, is that if you look at this in 2D, if we take the same example and we say, okay, our 64 tokens are actually on an 8x8 grid, and I want to do 4x4 sliding windows, and my tile sizes don't change, then the expected speedup drops from 3x to 2x. And the reason for that is what we label the curse of multidimensionality, which is that if you're still doing your tiling in 1D, then you're going to inevitably basically load a lot of tokens into memory that correspond to somewhere that's on the other side of the multidimensional space that you're dealing with. But the only reason you're loading it in is because, like, spatially, like in memory, they're close to each other, and that's how you're doing your tiling. So this can actually hurt your user experience a lot. And again, the best way to understand why is just flipping between these two examples. So over here, you can see that we're using many, many more tiles. We're visiting many, many more tiles. And this is what limits your speed up. So that was kind of the whole point of the faster neighborhood attention paper, where we introduced the FNA methodology, or fused neighborhood attention. And it's again an FMHA kernel. We took the Xformers FMHA kernel and we made some changes. The first one was multidimensional tiling. So if you're dealing with a one-dimensional attention problem, you just have a 4D tensor, literally, that's, batch, sequence length, heads, and headdim. You really don't change how tiling is done. But then if you step into the 2D problem, where instead of a sequence length, you have 2 dimensions, you have like an X and Y axis, then you no longer apply the same type of tiling where you go, okay, this is one tile, this is one tile, this is one tile, and you do it like that as if you had flattened your entire 2D grid. So what you do is you just look at what the tile shape in the kernel is, the tile size in the kernel is, let's say it's 64, and you reinterpret it as a multi-dimensional tile, like an 8x8. If you were doing 3D, you could reinterpret it as 4x4x4, or pretty much any numbers that, if you multiply, make up the original tile size. So by doing this, you're kind of making a hack in the kernel so that the tiling is done differently, but then the rest of the logic in the kernel, it's super hard to do this in newer FMHA kernels for like Hopper and Blackwell. So it's not always a super easy thing to do, but in that particular kernel, it was like somewhat easy because it was still in the Cutlass 2.x API. So it was really easy to do really hacky things. So what this ends up doing is it loads in tiles of Q and KV that still preserve spatial locality. So this minimizes the number of tiles. This just reduces the number of dot products, the number of flops that you waste, the number of dot products that you mask. And a second thing that we implemented was dynamic KV tiling. So like I said, if we go ahead and tile our entire context with some tile size, as long as there's even a single dot product in each tile that is not masked, you're supposed to visit it. So what this basically means is that for this dummy problem here, if we consider that the KVs that it's going to need to produce the attention outputs for just this one Q tile looks something like this, which it will, because this is sliding windows. So the KV region that you're going to be interested in is always going to be like a haloed version of your query tile. So if we need all of this, we don't save any compute. We end up visiting all of these tiles just to get this small region that could probably fit in a 2x2 or like 4 tiles. So we visit 9 tiles, all 9 tiles instead of 4 tiles. So the solution was we did dynamic KV tiling, which is you first go ahead and just crop that region out of memory. Not explicitly, you just offset your pointer, and then when you're like building your tensor object, you kind of pay attention to the fact that its bounds are now changed. Its bounds are no longer the shape that your QKV was. It's something smaller because you're like localizing it. So it's basically a different expression and an offset of the same tensor. So what dynamic KV tiling gives you is, well, it's a pain to try and visualize a block sparse mask for dynamic KV tiling, because you no longer like different Q tiles, depending on where you are, you no longer agree on where the tile bounds are, because everybody gets their own unique crop out first, and then they start tiling it. So it's a little bit painful to analyze, but it saves you more compute. Like in this case, it could very well just save you a lot of compute by skipping visiting all 9 tiles and only visit like 4 tiles. And then the second element of it was just the mask, right? We just took the same formula that we've been using to define neighborhood attention, and you basically plug it into the softmax/masking stage of your attention kernel. You just traverse everything, figure out what the original Q and KV coordinates were, and figure out whether this should be masked or not. But the problems with it were, first of all, like I said, we started with the Xformers FMHA kernel. So that was great because we could and still are supporting GPUs as old as Maxwell in Natin, which is this package that we ship all of our kernels in. So that was great at the time, but the state of the art, even at the time for Ampere, was flash attention 2. So because the performance upper bound of FA2 is better than FMHA, even if you're doing self-attention with an FNA kernel, you're going to see worse performance. So you're going to have to do a lot more sparsity to even compete in terms of speed. That was one problem. Another problem was the overhead of this multi-dimensional tiling, if you just implement it in software, can be very high. And the reason for that is it introduces a lot of software predication overhead that you simply cannot avoid and is really difficult to optimize. I didn't try too much, but I did make an effort for a while to further optimize it, and it was really difficult. And so in newer architectures, this wouldn't be a problem because you have hardware predication thanks to things like the TMA now. But at the same time, it still complicates the overall design of your kernel. You need to change a lot of code. You need to familiarize yourself with literally almost every line of code in what was a C++ kernel. So it's a big headache. A lot of things just break many other assumptions that are made in the kernel. So it introduces it requires you to make a lot of changes, and it's really difficult to optimize. And one way you can actually observe this is if you try to run those original FNA kernels and just give it like a two-dimensional or three-dimensional problem, but then switch it from like actually being flattened out to 1D to 2D to 3D. What I mean by that basically is like, let's say give it, I don't know, 10 to the, I don't know, 16K sequence length, and then reinterpret it as something that's 2D and then 3D, you will see the runtime increase just because of that extra software predication cost. But then the second biggest overhead was fine-grained masking. It's a lot of integer operations in a very, very critical part of your kernel, especially in newer architectures. So fine-grained masking itself can introduce some non-zero overhead to your kernel. And so the problem with this was, while it was a massive improvement on kernels that we had previously been shipping in Natin, which were our old naive kernels and later our gem-based but still unfused kernels, it was a massive improvement on those, but still, to people who are interested in realizing really good speedups compared to the best attention kernel that's out there, it wasn't simply doing enough, especially if you were to run this on Hopper or Blackwell. So I'm going to talk about the problem in sliding window attention in general that wastes flops first before I talk about how we address the issues in that FNA kernel. So, like I said, just this fine-grained masking, it's kind of easy to see that it hurts your throughput because you're paying for the flops, but you're not using them and you don't measure them in your flop measurements, right? So because of that, naturally, any type of sliding window attention is going to hurt your throughput. You're doing the same flops as something that's not a sliding window attention, let's say, some form that's perfectly block sparse. So you're not, so you might be doing the same flops in theory, but you're going to have a different throughput. You're going to have a different runtime because the other one might be wasting a lot of extra flops. So the way we attempt to solve this is by saying, okay, block detention is probably an extreme case, so can we do something that's kind of in between sliding window and block detention? And that's actually super easy to do. Like, the research had already been done in 2021 in this paper called HaloNet, again included in the end. Highly recommend you read it because they have an extended discussion on how applying this effect trades off translational equivariance, but sometimes you just have to do it for efficiency gain. So what we do is we added a new stride parameter to neighborhood attention. So we had kernel size, we had dilation, and now it has stride. And I seriously mean this. It could use padding. Like, I envision a padding API for it as well that might be like required by some applications. So what stride does is it basically has the same effect, very similar effect that convolution does, stride does in convolution. So it basically introduces a delay step in your sliding window. But another way of looking at it is that it groups queries together in that multidimensional space that we live in. And then those queries get to attend to the same window. So they are forced to share their neighborhood. So by that, and so the implication of that is if your stride is 1, then your query groups or your stride groups are just made of 1 query in them, so you'll still have standard neighborhood attention. But then if you set it to something like 2 by 2, then as you can see, these 2 by 2 groups of queries get to share their entire window. So that effectively introduces a delay in the sliding window. Again, similar to convolution. You can increase it further. And how they get to decide what their neighborhood is they elect some middle query, which again can be arbitrary. We just don't have the APIs for it yet. But you get to decide who's going to be the leader query. It's going to pick what the neighborhood's going to look like. And if we take it even a step further, just like in convolutions where you can increase stride up to the same value as kernel size and get non-overlapping windows, you can do the same thing here. And the non-overlapping windows here, surprise, it's just block detention. It's just window self-attention. So this basically means you can implement block detention even though you don't need to implement it with Natin. You can implement it with Natin today with neighborhood detention. Just set stride to window size. So that was like the first goal of this project that we did called Generalized Neighborhood Attention, which was we wanted to unify all of these patterns. It's no longer sliding window or blocked. It's just, no, I want the entire family. I want to decide exactly how much of that translational equivariance I trade off for performance, and I want to make sure I do get better performance, which is what I'll talk about next. So basically all of this is implemented and supported through, like I said, our Python package Natin today. And the freedom that it gives you is you're in charge of, you can decide what your token layout's going to look like in 1D, 2D, or 3D, in this case, like a 3D example. So again, we don't have an integer sequence length, we have a layout for our tokens, or really a shape that's a 12 by 16 by 20. It's like a 3D feature map. And for each dimension, you can freely choose your kernel size or window size as long as it's smaller than or equal to the input size. If it's equal, it's just self-attention. You can freely choose your stride value, which should be less than or equal to the kernel size, and you can freely choose your dilation as long as dilation times kernel size is smaller than or equal to your input size. And you also have causal masking support, which means you can, for instance, in applications where your token layout has like a time dimension, like let's say videos. You have 1 time dimension and 2 or more spatial dimensions. So you might want to have causal masking across time and not space. And you might not even want locality across time, or you might want less sparsity along time, but you want more sparsity in space. Again, all up to you. You have the freedom to do that, and we thoroughly test all of these against reference kernels to make sure that all of the kernels that we build and ship, all of the implementations are actually correct. And so let's talk about the effect of stride on speed. I'm going back to a 1D example because it's so much easier to understand it in 1D. So this is, again, the same problem that we saw before. It's 64 tokens, window size 16, Q tile size 8, KV tile size 4. So if you go ahead and just write this out and just count the number of tiles you save, you're saving 84 tiles out of 128. And that's why you don't get quite that 4x speed up, is because in order to get that, you have to save 96 tiles, or 3/4, whatever is proportional to your savings and flops. So with stride 1, you can't do that. Now let's see what stride 2 does. Well, one thing that's immediately visible is that the effect that stride has is very clearly just coarsening the sliding window effect. So it's really fine now. If you keep doing it, if you keep increasing stride, it's going to make it coarser and coarser. But the problem is, it's not a guarantee of saving you more compute. As you can kind of see, the actual speed up, or the expected speed up, is decreasing sometimes with increase in stride, because the number of tiles we're saving is decreasing. You can kind of see it happens right here. Like there's these 2 new ones that just because of these pesky tokens here have to suddenly visit that entire tile. So stride isn't always a plus, and it's not a guarantee to be. So at some point, though, you might end up with a stride that saves you more compute. And in this case, this is, excuse me, this is actually the perfect example, because you achieve full block sparsity. And what this means is you waste 0 flops. You don't even need the fine-grained masking. You can even disable it, save yourself some of that overhead. So this is actually pretty interesting. And this is also not blocked attention. So it's not blocked attention, but it can actually give you flop proportional speedup. So why even do block detention in this context? And that's why stride is such a powerful new parameter, is that there are forms of local attention that are less coarse than block detention, and the coarser it is, the less the quality. That's at least the argument. So if you can have something that's less coarse, trades off less quality than block detention, but saves you the same amount of compute, why not just use that? But this is where it gets complicated. With 1D, no dilation, nothing like that, it was pretty simple to see. But what about 2D and 3D problems? What about when there's dilation? What about problems that aren't evenly divisible by these tile sizes? What if I do something like dynamic KV tiling in our old FNA kernel versus static KV tiling? What if I'm not even doing multidimensional tiling? What if I want to do a study of, do we even need multidimensional tiling, let's say? And I haven't done that study, by the way. But so what if we want to do something like that? And we have so many parameters in GNA, or neighborhood attention NATN itself. You're in charge of what window size is, stride, dilation, causal masking. That's also assuming you know what your input sizes are. You might just be the architect of, like, a deep learning architect of a new architecture for some application, and you might have some freedom over what your input tensors are going to look like. It could, measure into your, I don't know, pre-processing or something like that. But anyway, you have a lot of variables that determine how much compute you end up saving. So we really wanted to be able to study the performance implications of these without having to write kernels and actually run them, or even having to run kernels. So before we even started working on any new implementation or kernels, we started with this analytical study. And so what we came up with is a simple program that we call NATN simulator. And what it does is it takes in all of those variables, your use case, what are your tensor shapes, window size, stride, dilation, etc. And it also takes in kernel design choices. It can be for a kernel that already exists. It can be for a kernel that you're planning to work on. What if it's pretty reasonable to ask, okay, let's see what the returns can look like before I decide if it's even worth my time to work on this kernel. And all that this program does is, given those variables, it's just going to report the number of inner loop iterations, or KV tiles, for each query tile. And you can use those statistics and, I don't know, you can average it or take the maximum, just the worst case scenario. And if you're issuing only a single wave, then taking the maximum makes sense, but in some other cases it might not. But it's the worst case scenario. So you can safely take the maximum of these inner loop iterations, or KV tiles, overall query tiles, and then use that to compute a speedup over full self-attention, which would visit all of those tiles. And so the entire argument here is that your actual speedup that you're going to feel if you write something with very limited implementation overhead is going to be very close to savings in terms of tiles and not flops, obviously. So that was the whole point of doing this. And it's actually pretty effective. So, excuse me, the visualization that we're doing here, which is from our paper, we're applying a very strong filter. So in this case, we knew our target was, let's say, Hoonian video. It's a popular video generation model. And we knew we wanted to, let's say, introduce 91% sparsity. We knew a few details about, okay, what if we implement this kernel on this hardware? The hardware in question was Blackwell. And we knew some things about the tile sizes and shapes, but what we did not know, once we settled all of those, is what stride we were going to use. So you can simply run the simulator, just run an entire sweep on all possible stride values. It's not going to even take that long. And you will have results for that. But then visualizing all of that can be confusing at times, because, like we just saw, an increase in stride is not a guarantee in speedup. So we applied a very strong filter here so that we only see cases where an increase in stride is at least giving us better performance. So we're just going to exclude everything else. And as soon as you hit that perfect speedup, that flop-wise speedup that you can't even get better than, then there's no point in even continuing the search. So as soon as you hit the smallest stride that can give you perfect block sparsity, you win. You have a stride value that you can go and experiment with. Now, if your application is too sensitive to this, then you can choose some of these stride values that make sense to you and do some mini experiments and see how far they'll get you. But then again, the point of this is you don't need to run the kernel over and over again if there is a kernel. to figure any of this out. This is just giving you speedups, and you can use these speedups very easily to you can translate them to end-to-end improvements, and that way you can justify whether you need a new kernel, whether the existing ones are going to be enough for you, because once most of these details are settled out, you can just go ahead and run it. But anyway, so this is what this simulator can produce for you, and it's actually pretty useful. So now I'll quickly shift into our new Hopper and Blackwell FNA kernels, unless there's any questions with everything else and the new design choices that we're adopting.
Yeah, Lee, like the main thing that popped in my head as you were talking was like you're talking quite a bit about like Natin doesn't seem to be like a kernel. It's like more like a kernel generator, like basically given like an algorithm like generate like the fast kernels for it, depending on some trade-offs between like stride and you want like whether you want block sparsity or like neighborhood sparsity. So it sounds the most similar to something like flex attention to me. Like, and I'm sort of curious if you thought about like the trade-offs between the two libraries.
Right. So two things. One, it's not a kernel generation tool by any means. So we take primarily today, all of our kernels are in Cutlass. So we take Cutlass kernels and we modify them, and we introduce this whole, like today we only have fused kernels. So today we basically have a bunch of those FNA kernels just with different design choices that are based on attention kernels from Cutlass. And so the rest of Natin is just about doing whatever extra tools that are going to be necessary to run all of these. And so the difference with flex attention is exactly that it doesn't allow arbitrary masks. You can only use masks that are compatible with like how neighborhood attention is defined and set up. So at some point, the two might converge, because we do keep trying to generalize the neighborhood attention formula further and further and add new features. So at some point, it's possible that the two might converge to the same place. But my understanding of how flex attention works, and I might be wrong there, is, well, either like if you want to do something like flex attention, you either bake some static attention mask into your kernel, which can be limiting, or you just develop a kernel that loads in a block sparse mask, or can at least do the block sparse parts on the fly, and then loads in the fine grain mask from memory. There's a lot of design choices there. So it is possible for these two to converge, but where we're kind of going with Natin is that we want to approach something that can potentially give you zero overhead. So you don't really, so you can run pretty much any use case that fits within that family of attention patterns. And at the same time, you don't have to need to compile them, and there's a guarantee that you don't load any explicit mask from memory or something like that. So like I said, it is possible for the two to converge, but no, how they end up delivering the performance and running looks very different today. But by the way, we do have a flex backend too. We've just disabled the compilation part of it because it doesn't pass all of our unit tests. Might be a bug that we're trying to figure out. But yeah, sorry, what were you gonna say?
So it seems to me like, I mean, typically when, I guess in your community, when you guys say block attention, you mean dependencies like between the current block and the previous block. But I think if you generalize, like let's say arbitrary blocks, plus you allow a neighborhood attention, which can go from a neighborhood of nothing to a neighborhood of your whole matrix, it seems like you can cover a fairly powerful range of attention masks with just block sparsity and neighborhood attention.
Right. Yeah, exactly. You can. So with neighborhood attention, you can, like I said, neighborhood attention itself without stride is never fully block sparse unless like you're doing self attention with it. So unless certain conditions are met, it's never fully block sparse. But yeah, today it gives you the freedom to like enjoy speedups. Again, on Hopper and Blackwell, you can actually realize that with respect to modern kernels. On Ampere, it's a little bit limited. We're working on that. But so it gives you the freedom to run whatever you want. And unless it's some edge case where you have a really huge window size that is like impossible to get any kind of savings out of that, unless you're one of those exceptions, you're also going to see really good speedups over it. But no, it's still not an arbitrary mask, because there are a lot of patterns that you can come up with that are not implementable today. Our hope is that we can support as many of those as possible. But then at some point, you might just want to pick your sparse pattern at runtime. Like if you want something that's like circular or something like that, then it really falls out of what the neighborhood attention formula gives you. So there's still some assumptions that we make with respect to what our block sparsity looks like that, again, over time we're going to try and relax. And I hope I can work on this project long enough to support arbitrary mass, and at that point it will be really interesting if this and flex solutions like flex can kind of come together and just be one solution.
Cool. Thanks, Ali. That's it for me.
Of course. Great. So to talk about these two kernels, which I personally myself believe that I would sooner graduate and finish my PhD than be able to work on both of these. But so a while ago, we had a curious thought, and so it kind of originated from seeing a few implementations of NAT and flex attention. And that kind of actually started with a conversation I might have had from anyway, it doesn't matter. So what we kind of thought about is that if we could simplify the design of our kernel by paying a tiny bit of by paying the tiny cost of like a small memory operation ahead of the attention operation, if we could afford that, then we should really consider it, because it would simplify the design of the kernel. It would simplify a lot of things. It would open up a lot of doors. So that's what we considered. And at the time, we were dealing with only the Cosmos and Hunyan use cases. So we basically executed, I believe, Cudian and Cutlass attention at the time on a Blackwell GPU on those problem shapes. And so we collected the runtimes. Then we figured, okay, if you're doing FP16, and if we consider the size of your QKV and output tensors and the data type they're in, all of that, if we consider that we can write a memory copy or just a copy kernel that can almost fully saturate the 8 terabytes per second bandwidth that you have on a B200, then it would take less than 1% of the full self-attention time to rearrange all of your tokens once. And it doesn't really matter that it's really difficult, maybe near impossible, to fully saturate that 8 terabytes per second, at least in all use cases. But 1% was still like really small. And again, in some the more you don't improve it, the worse it's going to get. But at least on the scale of problems that we were dealing with, it seemed like a pretty reasonable cost, considering that if you don't do it and you try to do token permutation, even though you do hardware predication, you don't know if that's going to be without any overhead. And not to mention, you're going to have to change a lot more in the attention kernel to get it to happen. So at any point, you might introduce some unavoidable overhead. So that's basically what we thought about. And so the way you actually do this is relatively simple, at least conceptually, is that you can perform that static multidimensional tiling and just apply a copy operation to kind of flatten those tiles. And this kind of simulates the multidimensional tiling without the kernel actually even being aware of it or having anything to do with it, is more accurate. So in this example, for instance, suppose this is our 2D grid of tokens. It's 4x4. And if we take just this one tile and flatten it and store it in memory like this, then we know that whatever tiles our attention kernel ends up loading are going to preserve spatial locality. So that's pretty much all we need to do to break free from that curse of multidimensionality. So the pros of this are makes your implementation simpler, like I just said. So you can make very few changes to your FMHA kernel and get this to pass all of your tests. And at the same time, there's no more extra software predication. It doesn't even matter if you could relay it to hardware. You just don't need to do it because it's a memory operation that you do ahead of time. The problem with it, though, is, well, you always have to do that memory operation, and it's repeatable, it's exposed, and it might be hard to get rid of in some cases. But in many cases, you can actually reduce this to only occur twice in your model. You do permutation once in the very beginning and unpermute once in the very end, because many use cases might not, as long as you're not using dilation, basically, and as long as you're just dealing with a typical transformer, you're just doing attention MLP, attention linear layer, etc., then you're fully invariant to permutation, or equivariant might be more correct. But anyway, permutation really doesn't matter. So the rest of your model doesn't really care. The only thing that cares about it is the neighborhood attention in it, and even self-attention wouldn't care about it. Again, unless there's padding you need to do, there are some exceptions. But in many cases, you can just factor out this token permutation, do it once in the very beginning, and then undo it once in the end. And this will minimize the overhead from that memory operation. We don't do that ever in practice yet, but there's a lot of work to be done on optimizing token permute. But anyway, so we were able to, just by changing our approach to how we implement FNA kernels, we were able to develop kernels a lot faster. So very quickly, we had Blackwell kernels, and then we had Hopper kernels. And so now this is kind of what performance looks like, is that in a lot of these cases that we studied in the GNA paper, you can actually, if you exclude the memory operations, you can get speed up that's proportional to your sparsity level. And the reason why this is interesting is that it's effectively showing that there's very little overhead from just implementing that extra block sparsity. And that's what we were really aiming for. Because like I said, the memory operation, a lot of times you might be able to minimize it. And again, even it might not even be that big a percentage in your end-to-end workload. And on Blackwell, it looks a little bit similar. The speedups that you get do decrease a little bit in some cases, but again, in all but one use case, you still hit that flop proportional speedup. This is all operation level. So how much can it be end-to-end? Well, like any other sparse attention approach, or most is more accurate. If you're prepared to train it, you can introduce more sparsity naturally, right? So the larger the share of self-attention in your workload and the higher sparsity you can introduce, well, the more your returns are. But if you can't train, then the amount of sparsity that you can introduce is going to be limited, whether the percentage of sparsity or whether you consider how many layers you introduce it into, or attention heads, or in case of diffusion models, diffusion steps. So I'm including a table from our paper here where we show this kind of on Cosmos, different settings, not as many settings as are possible, that would be huge, but primarily 4 different settings. So 2 levels of sparsity, roughly 50% and roughly 90%, and then 2 settings, one where you apply sparsity to all the diffusion steps, and one where you hold out a few self-attention steps just to get better quality. And these will have different visual results, and some of them might be more acceptable than others, and some of them less. For instance, with Cosmos, we couldn't introduce too much sparsity, but with Hunyan, it was more. But anyway, we're more curious about the speedups that you can get. And so in the paper, another thing that we did is we also reported our expected flop-wise end-to-end speedup. So if we were to assume that these are all 56% sparse attention layers, then your speedup would be, in terms of flop, would be super easy to calculate, because you can calculate your flop-wise sparsity. It's just 1 over 1 minus 56%, or 100% minus 56%. But anyway, we specifically included to show that it is really easy to have multiple different sparse attention methods, which is kind of the whole point of Stride. It could implement block attention for you too. And their flop-wise speedup is going to be identical, but it's not really a good measure, because you should really look at how many tiles you save, what percentage of block sparsity you achieve, basically. And so that's why that ended up being very useful. And it was also a useful measure for comparing our actual end-to-end runtimes to some analytical figure to see, okay, how much more improvement can we make to this thing? And so with Cosmos, like I said, it was more limited. With Hunyan, what was also interesting is that the percentage of the workload that was spent on those memory operations was so little that we didn't even have to make any optimizations. In a lot of cases, we would achieve a speed up that would basically the speed up, the difference between the theoretical versus actual speed up would be within the margin of error of each runtime that you get. So in a lot of cases, we basically got flop proportional speed up, at least end to end, that we were expecting. And so I'm going to talk about one use case that we did recently. It was part of my summer internship at NVIDIA, where we took the recent Cosmos Predict 2 models, and this time we trained it with sparsity. And this was kind of a case in point that if you're prepared to train, you can kick things up a lot. So what we did was we used both types of attention that, at least in terms of receptive field, that neighborhood attention can give you, both local forms of NA and dilated forms. And the approach we had for introducing this into the existing architecture was we just took the model that was trained with full self-attention, and we basically started measuring how much error is introduced by various sparse attention patterns, most of which we got from just the NAT and SIM program. So we had a curated list of different sparsity levels, different, there were forms that were dilated, there were forms that were a mixture of dilated and striated, there were various kinds, and all of them were block sparse. So we basically just looked at how much error would be introduced with respect to self-attention at each layer. You can make it more fine-grained and do headwise. We just didn't have time to do that. So if you do it layer-wise, it's still pretty successful. And then experimentally, we came up with a threshold for that error where we said, okay, anything that's within this threshold, we're just going to pick the highest level of sparsity that is within this threshold. And it was actually pretty successful. Like, you didn't even have to train it that long, typically for a fraction of what the original model had been trained for, but you just resume training and it relatively quickly recovers the additional loss that's introduced. And the end result that it gives you is, and this was cross GPU architecture. So we had measurements for various Hopper GPUs and also the B200, which is the Blackwell GPU. And of course, there were variants. There's a 2 billion variant and a 14 billion variant. The attention workflows were different. And there was a 10 FPS and 16 FPS variant too. So lots of different variants, but you could get really good speedups. Like with the 2B variant, you could get anywhere from 1.9 to 2.6x end-to-end speedup, and with the 14B, 1.7 to 2.1x. That's just because the share of attention was just lower in the 14B model. So it went pretty great, at least in terms of these statistics. But quality-wise, we also observed that, well, while they can't reproduce identical videos or worlds that you can take the difference with and do further analysis on, because these are different checkpoints of the same model, quality was seemingly mostly not affected in a lot of the samples that we went through, and even in the benchmark scores that we had. So if you're interested in this, I'll include a link to this project as well in the end, and keep an eye out for further reports on this. And so I'm just going to quickly skip through the slides here that kind of show the samples, but I feel like there's a lot of videos out there that you could just refer to for that. So that's the end of my slides. If there's any questions, I'll take them now. Otherwise, I'll just move on to going over the code in the live demo.
Thank you, Lee. Yeah, so I think a lot of the questions have been already responded to by your colleague Aditya Kane in chat. So I think we can probably keep going.
Okay, great. So perfect. So let me, okay, I'm still sharing this window. Let me go ahead and share my terminal. Okay, so are you seeing my terminal? Oops, what happened? Oh,
yeah,
can you see
yes.
Is everything readable? Do I need to make the font size bigger?
Maybe a tad bigger.
How's it now?
Okay, so it works.
Okay, great. So I'm just going to quickly go over a few things in Natin. There's not enough time for me to go through all of it, but in case you're curious about any part of it, so the organization of it is relatively simple. We have a CSRC directory where it's all of our CUDA C++ code that we built into what we call libnatin. If you're not a CUDA user, you're not going to be dealing with this, because the only implementation, the only backend that we have for non-CUDA users currently is just our Flex backend, and that's just in pure Python/PyTorch. And then there's our Python package here. You can choose to run our unit tests and mess around with them, especially if you're trying to add an optimization. PRs are very welcome. But also there's some scripts that can help you change the autogen granularity to generate more build targets or fewer to like optimize your build time, or basically stamp out instantiations with tile sizes that we don't currently ship Natin with. So I'll quickly just go through Natin itself as like just if you're an end user, we offer obviously like the various neighborhood attention functions. You have maybe sorry, I'm just thinking maybe it's easier to just go through these quickly if I share my browser. and go through our docs. So if you're an end user interested in Natin, I'll go ahead and share this. I hope everybody's seeing my browser. At least that's what it looks like there. Okay, so if you're an end user, please visit our website. It's just packed with documentation, and we try to keep improving this as much as we can. So if you're an end user, what you would use is either our torch modules or operations. We have like 1D, 2D, and 3D neighbor detention functions that you can call, do backprop on whatever you want. And then we have just standard attention. And the reason why we pack our own attention kernels, like full self-attention kernels, is that we have some APIs for doing neighborhood cross-attention, which is just standard neighborhood attention, some cross-attention, and then you do merge attentions, similar to what you would do with context parallel. So we offer APIs for those in case you want to run those. We also have fast paths. So if at any point we detect that your problem is actually a self-attention problem, it's just going to run a self-attention kernel instead of like an FMHA kernel instead of an FNA kernel. But anyway, like whether you want to do 1D, 2D, or 3D problems, you can just simply call these operators or use our torch modules, whichever one fits your needs better. There's some examples of what like the signatures are and how you're supposed to pass arguments to them. And then you have like some primary parameters that are just related to just the attention, the type of attention that you're trying to run. So obviously kernel size, stride, dilation, causal, what have you, the attention scale, that additional cross attention that I mentioned. And there's also other parameters. These are all performance knobs. And some of them apply to only certain backends that we have. And so if you want to get the best performance, you would go around and play with these. We also have a profiling toolkit that kind of automates some of that. Eventually, we're going to just keep improving the experience of this so that the defaults give you close to what's the best performance, but you can obviously always go beyond that. And so primarily the things to look out for are what's the backend. And like I said, we have our Cutlass FNA/FMHA, which is the same FNA kernels we did last year that I said, well, obviously has that token, has that software predication overhead. And so performance might not be as good as you might expect. We also note that in our backend pages. But then there's also our Hopper FNA or FMHA backend and Blackwell backend. And these can get you very good performance. And we also have both functions that you can call with your input tensors that can return a list of all the configurations. Those are mostly just tile sizes and some additional knobs if the kernel has them. So you can use these interfaces to figure out what tile shapes we even support currently. And if there's some tile size or shape that might be valid that you might want to try that's not currently supported, we can obviously add those. You might be able to just add those and build Natin from source. But anyway, like this will be like an entry point for that. But again, like the profiling toolkit also gives you that. This is just an easier way to do it through Python code and not have to deal with the CLI. Similarly, with our Flex backend, we have like similar functions that give you these valid choices for these performance knobs that you can use. The biggest thing that I encourage folks who are interested to play around with is our profiling toolkit, which is not anything too complicated. It's using the PyTorch profiler under the hood. But what it does is you can give it problem shapes and problem sizes and window sizes and strides and all of these. Pretty much most of the use case information and knobs that we support, you can give it, and you can just experiment and see what the result looks like. It has a dry run mode that just prints out all the, like I said, valid values for those performance knobs that are supported for every backend that's supported for your use case. You can run the optimize mode, which will basically pick the best backend for your use case that's available and run through all of the performance knobs and select the best performing ones. With some backends like our Cutlass FNA, FMHA backend, where we have a lot more configs, it's going to take a lot of time to do that. So use it smartly. But eventually, the simulator program that we use, we intend to integrate it into the profiler so that instead of running over all of these configurations, you can at least reduce your problem space a little bit by figuring out at least what tiles give you the best statistics. So I'm going to stop this here and just go back to the terminal now. But if there's questions, feel free to ask. There we go. Okay, so I trust my terminal is visible again. Okay, there we go. So within that, and how we kind of separate out all these concerns is that the entry point, those that attention and neighborhood attention functions that we have, basically just check all of your inputs and make sure that the backend supported if you're specifying a backend, and if not, we'll select a backend for you. And then eventually they'll call into the individual functions for those backends. So if you choose Blackwell FMHA and your device supports it, or if it's chosen for you, if you didn't specify anything, it'll call that, and similarly everything else. But then the backends themselves, we like separate out into this part of the package where, well, they might have their own, they actually do vary a lot in even how their autograd functions are constructed. So like the original FNA doesn't have token permute in it. So it just, like its autograd function is pretty straightforward. It just calls in the C++ function that is going to launch the kernel for both forward pass and backward pass. Like I said, it doesn't do any explicit memory operations, implements pretty much everything like a champ without even raising any issues or needing any extra operations. That's like the mindset. But then if you look at something like, let's say, Blackwell FNA, then it looks a little bit different because we have this token permute bit right here. So in your forward pass, you have to do token permutes, and token permute is comprised of, well, you might need to pad it first before you can do the permute. And then the way we define token permute, which I'll later show you, is specifically checked to make sure that we perform one memory copy operation and nothing more. And like I said, it's in pure PyTorch right now. We might end up having custom copy kernels for this to utilize more of the bandwidth, because I think on Blackwell especially, it's like not that great. It's like 1/8 of the bandwidth that's available. But still, like, it might not be as easy as we think. But again, if you're curious and you're interested in copy kernels, and you're interested in contributing, this might be one area you can improve. And so anyway, once we perform token permute, we basically have query, key, value, everything, a permuted version of them. And these are all going to be 4D tensors. So if you're doing one-dimensional neighborhood attention, you basically have a 4D tensor comprised of, well, batch, sequence length, heads, head dim. So you always have that 3 dimensions for batch and heads and head dim. But then if you're doing 1D, then you only have 1 additional dimension for your tokens. If you're doing 2D, it's going to be 2, and 3D 3. So you end up, we pretty much everywhere assert that all of these tensors are like either rank 4, 5, or 6. So, and based on that, we determine what type of neighborhood attention you wanted. So the thing here is that the inputs to this kernel here that is going to be run is just going to be a bunch of 4D tensors, because we're doing token permutation. So again, we're keeping a copy of the original QKV shape before we pad it, before we do token permute or anything. And later in the kernel, we use this to figure out our block sparse mask and fine grained mask. And then once you're done, you just token unpermute or reverse the permutation for whatever your output was. In the forward pass, that's just output in log some x. And in the backrop, it's just going to be gradients for q, k, and v. So in the backward pass, is actually a little bit more complicated. And you also have to repeat token permute for some of the same tensors like q, k, v, and output. And the reason why you have to do this is that there's no guarantee your tile shapes in the forward and backward pass are the same. In a lot of cases, that might not even end up being true. But like another easy optimization here that I only noticed this morning was, well, we can check, and if the tile sizes in forward and backward pass are the same, you can just kind of cache that permuted tensor instead of the original. Save yourself some time. But anyway, in the backward pass, you just pretty much undo that. And token permute itself, it just lives here. It's very simple, all in PyTorch code. And then there's the padding and unpadding, and then there's token permute and unpermute. I'm not going to go too much into details here. I don't think it would be that much helpful, but if you're curious, feel free to read it. And yeah, whenever we do any kind of tensor view or transformation, we specifically make sure the pointer doesn't change to make sure that we're not introducing any extra copies. And so I'll quickly go over how we organize just the backends, because I don't think going through the kernels might be, again, that helpful unless you have prior context. But so what we do is, because this is all based on cutless and C++ and specifically templated C++, no kernel is actually just a target that you can launch. Most kernels are templates, and once you instantiate them, they're only good for one use case. Like, you have to instantiate it based on tile size, basically anything that's static, like tile size, data type, and etc. So we keep our instantiations under a separate autogen directory, and it's not useful to look through this at all, because it's just instantiations that's basically repeated code. This is just so the build system goes and compiles all of these. And the reason why we auto-generate them is exactly that. Over time, the number of kernels that we ship have varied. So we typically try to have many build targets, but not too many, but enough that if you're building this on a DGX box, which I usually do, you really want to use all of those threads and workers that you have available to maximize your parallelism so that it builds quickly. But anyway, if you want to look at the kernels, just go into the header directory, just go into include and then CUDA, because the rest is just the wrappers. And then over there, you will find like references. FMHA is the Xformers FMHA kernel, slightly adapted, and FMHA Blackwell and FMHA Hopper are the Cutlass examples for Hopper and Blackwell. The naming will have to change because it is really confusing at the moment. And not to mention, we like in the package itself, we call FMHA Cutlass FMHA, but these are all Cutlass. But anyway, we have like equivalents for all of these. We have FNA, Blackwell FNA, and Hopper FNA. And right now, there's a lot of code duplication that might be unnecessary that we'll optimize in the future. But primarily, excuse me, the difference that you will find, I'll just, let me just go through Blackwell since that's what the demo is. So in Blackwell, what we basically do is we still have the static multi-dimensional Q and KV tile shape, in addition to the original kernel tile shape that the FMHA kernel would need. And so by having those tile shapes and by them being static, we can actually offload a lot of the things that we do to Qt, which is the reason why there's so little implementation overhead here, because it's doing everything very efficiently. But then the only, excuse me, other thing that changes is that inputs to the kernel, in addition to like all of the tensors and the problem shapes and everything, include your Q and KV shape post token permutation and dilation, post token permutation and padding, as well as the original QKV shape, because you need to mask out elements that are out of bounds, otherwise you're accumulating garbage, and your results will end up being incorrect. But then you also have window size, stride, dilation, pretty much everything that you would expect with neighborhood attention. And then the rest of it is actually pretty simple, because the way it actually works is that you, like I said, you're only going to change two things. One is the number of iterations and what those iterations correspond to. There's inner loop iterations. And the second thing that you do is you do fine-grained masking. And so if I want to show what this looks like in the forward pass kernel, I'll quickly go into the the load collective for the forward pass. So over here, basically what we do is, like, right when we're trying to predict how many iterations we're going to process, we have this helper. We have this kind of mask object similar to the FMHA masks that are in both Hopper and Blackwell Cutlass examples for attention. So there's this mask object that is going to have all the routines that we need to easily figure out, okay, how many KV tiles do we have, and do I need to mask this element out or not? So we basically use that where we implement a get trip count, and I'm just going to open this right here so that it's visible, so it's obvious what we're doing. So get trip count, what it basically does is, and this is a little bit not so, this is not the cleanest code I've written, but in fact, it's very far from that, but it gets the job done. I'll clean it up later. But basically what it does is, so you know the block coordinates of this parallel work tile of work. And based on that, you know that, so based on that, you can get like the 0th coordinate just corresponds to the query index. So you have to map that to which query tile it is. So basically what you're doing is you're figuring out the coordinates of the first and last query tokens that are in your multi-dimensional tile. So once you figure that out, then you call pretty much if you go through all of our C++ code, even our Flex implementation, you will see this naming pattern reappear: get window start and get window end. These are just formulas that we've tested over and over again that are correct neighborhood attention behavior. So get window start just basically gives you where your context window is supposed to start. It takes in your coordinates, window size, stride, and the shape of your problem. And it basically just gives you the coordinates of the first KV token that you need to visit. And there's also get window end likewise. So what we do is we figure out the first query in the tile, and the last query in the tile is just the first query plus tile size, and then just subtract 1. So we figure out the first query, the last query. First query, you need the window start, and last query, you only need the window end, but it's easier to do window end once you know what window start is. If you're not causal, it's just an offset, and if you're causal, it's just yourself. But anyway, I won't get into too much detail there, but you figure out the coordinates of your first and last KV coordinates, and this is the part where static KV tiling is going to hurt, is that you have to floor your KV start to something that's a multiple of your KV tile size or shape. And similarly with your last KV, you have to seal it you basically round it to the nearest integer. You basically increase it to the nearest integer that's divisible by your tile size. So what you're basically doing here is you're figuring out the coordinates of the tiles that you need to visit. And then you just subtract them, you take their difference, and that tells you exactly how many multi-dimensional tiles you're going to visit. So if you're doing a 3D problem, this is not going to be an integer, it's going to be a 2x4, let's say. You're going to need to visit 2 tile, you're going to start here and you're going to visit 2 tiles along the y-axis or x-axis and 4 along the y-axis. But so we basically just return these 2 things. We return where's the first query tile that you need to start, and how many tiles do you need to visit. And based on this information, pretty much in most fuse attention kernels that I've seen, there is like a global inner loop iteration counter somewhere. All you do, and the reason for that is, well, for causal masking and for standard 1D sliding windows, if it's supported, you're going to need that anyway. So there's always something that is written in a way that's easy to modify so that you can get basically block sparsity. So over here, that's tile count or mask tile count. Although I don't think the name is particularly helpful. I'm not sure if this was in the original or it's something I read. Anyway, you figure out how many iterations you need to do. So by just using size, you take the product of all the numbers in that number of tiles or shape tuple representing the tiles that you need to visit. By just taking the product of those elements, you figure out how many tiles there are. So that way you just limit your inner for loop. You limit the number of iterations there. And then the way you figure out which tile you're going to visit, that's where you need to make sure that the underlying kernel does not make any there's no design choices made that simply assumes that you're always going to visit tiles in order, and that can kind of screw things up a lot. So you need to whatever kernel you're working with needs to already have support for visiting tiles out of order, and luckily the TMAE does support that. So it's actually it's incredibly easy to do within the Qt framework. So what we basically do is we create, and in the Hopper version, this looks a little nicer because I do it with Lambda functions. But so what we basically do is we figure out what tiles we need to visit, and we construct a mapping via Qt that takes in iteration index, that's an integer, right? And you always have that iteration index, but it maps it to a coordinate. It maps it to a coordinate of the tile that you're going to need to visit. And then it figures out, according to the token permutation that we did, where was that tile? What's the tile index corresponding to that? And it maps that coordinate back to that index. So iteration 0 might be mapped to tile number 18. and 18 will depend on like what your tile sizes are and how you did your token permutation, basically. But that's basically all you need to do, is that every wherever you're wherever you're issuing memory loads from your KV, or in the backward pass that would be Q, wherever you're issuing those, all you do is you modify the offset, you modify the coordinates that you're accessing, and that's all you do. And that can be done very efficiently with very limited overhead, at least in this case. So the only part that's remaining is the mask part, the fine-grained masking part. And this one's a little bit different depending on which kernel you look at. So in some of these kernels, and it also varies between forward pass and backward pass. In some of them, you can make some assumptions like every thread owns an entire row of the attention weight matrix, or whatever tile of it we're working with. So if you know you're only dealing with one tile, then your query coordinate is not going to change for that one thread. So for that one query, and this is the case in the Blackwell forward pass kernel. So over there, we don't try to map all, because it is really expensive to map these indices corresponding to Q and K back to coordinates that you actually need for your neighborhood attention mask. So what we end up doing is, because we can make this assumption, because this is how the kernel is structured and how ownerships are structured, we can actually simplify it a lot and just have the one query coordinate once, figure out what its window start and window end are, and then only do that reverse mapping back to the coordinates for individual KVs that we visit. And then finally, we just have this function that just checks the bounds. So if it's within the KV start and KV end bounds, it doesn't mask it. Otherwise, it ends up masking it to negative infinity. And that's basically how it works. So unless there's any other questions, I'll stop going over the code now and just do a quick demo via the profiler.
I think the demo, let's just go with the demo.
Okay, great. So what I've got set up here is I'm just renting this cloud Blackwell GPU, and so what I have here is I'm just going to run a 3D example. So let me just go ahead and do that. So this problem, so I'm calling just the NatN profiler, and I'm not changing the batch from 1. I'm just doing 24 attention heads, 128 head dim. And the tensor shape is 30 by 48 by 80. And this is the same tensor shape that we had in our Hoonian video use case back when we did the GNA paper. So what I'm going to do first is I'm going to run it by just setting the backend to cuDNN. So we're trying to improve this, but this is like support for third-party attention kernels. So right now it only supports whatever Torch SDPA gives you, which is cuDNN, Xformers, and Flash Attention 2. But over time, we might add support for other third-party packages like Flash Attention itself, so you can just directly run those within the profiler and like see the results in a similar way. So when you explicitly set your backend to something that's not a NatN backend, it's just going to ignore if you give it any window size or anything. But by default, the window size is just the input size. So if you don't specify a window size, it's just going to run self-attention. So this is cuDNN performance. And I'll go ahead and just, in the interest of time, do forward and back prop at the same time. So in the forward pass, this is the performance you can get with cuDNN through PyTorch today. On this use case, it's about 140 milliseconds. And if I enable backprop, so forward pass is another reason why we kind of started shipping this, is that I find it useful to like categorize all of these to make sure I don't have to rely on reading the symbol or the symbol name or operation name to figure out what kernel this is. So the backprop attention kernel is about 532 milliseconds. Forward is about, so it varies actually a little bit. So like 130 to 140 milliseconds. But then let's just take away that backend, which means it'll just try to select the best backend in NatN, which in this case, because it's attention and it's Blackwell, it'll be Cutlass's Blackwell FMHA. So this should give you like somewhat similar performance. It's actually a little bit different. So the forward pass is kind of a wash, a little worse probably, but the backward pass is a little bit faster. So these are just the Cutlass FMHA forward and backward kernels. And with cuDNN, I'm sure there's like some further auto tuning that can be done that either I'm not familiar with or might not even be in the SDPA API. So what I want to do is now start localizing this. And I'm going to just work on that one use case from the paper, which was like roughly 90% sparsity. So I believe the window size was 18, 24, 24, but I'm going to double check real quick just to make sure. Yes, it's 18, 24, 24. So I'm just going to run this again without changing any of the defaults. So I'm not even touching those performance knobs that I mentioned. So you can see like runtime in the forward pass, and you can also see these extra operations. These are just token permute. A lot of these. Some of these might be related to padding. Some of these might be token permute. Might be and some of these actually, because this is backward pass, one of these might be workspace initialization. Anyway. So over here, if we want to just look at operation level and not include the cost of the memory operations, our baseline is like 131, and we're accelerating it down to like roughly 43 milliseconds. That's like roughly 3x speed up. So pretty much what we expected. And in backward, we're doing 396 divided by 79.57. That's roughly like 5x. So you can kind of see with 90% sparsity, you're not getting your 10x with standard sliding window. So let's go ahead and introduce stride. So the stride value we used for this that was perfectly block sparse was 1688. So let's go ahead and try that real quick. So you can see there's a huge drop in the forward pass, also in the backward pass, but actually, yeah, in the backward pass, it might be close to, yeah, in both cases, it's like close to almost like 2x, maybe 1.9. But like, at this point, I'm going to just rely mostly on the total runtime, everything included. And so you can see over just our own baseline, which is the Cutlass FMHA example, that's 529 milliseconds roughly. And so standard neighborhood attention gets you roughly like 3.75x. If you consider both the single forward prop and backward prop. And if we compare to the strided use case, that's like 90, almost 94 milliseconds. So that's like 5.6. But there's also the optimize feature. So I'm just going to quickly demo the dry run feature, which doesn't run anything. It just reports all the knobs that you have. So it goes through and it says, okay, your use case is compatible with Blackwell FNA, meaning I have a Blackwell GPU, and this problem size and everything else is compatible, and data type and everything else pretty much. And it gives me all of these performance knobs that I can use in Natin. And I can choose to search these however I like. I can later, when we have the Natin simulator, you can just run that through it, or you can just pick one that you think would be best. Same thing with the Cutlass FNA backend, which again is compatible, although we truncate the results because there's too much of them. Again, just read the docs. It's super easy to explore all of them. And then also almost everything's compatible with Flex. But then let's try, I don't want to even think about those. I just want this to run all of them and pick the best one. So if we do that, it's just going to search through all the valid configs that it can find for forward and backward pass, and it can sometimes make quite a bit of difference, especially if there's padding effects and things. So our runtime used to be 93, 94 milliseconds, and now all of a sudden it's like less than 70 milliseconds. Like the forward pass runtime drops from 25 milliseconds to roughly 14, which is a lot. Same thing with backward pass. And the reason why I chose this example specifically is that I knew this would happen because the default tile sizes will introduce a lot of padding into this, but also because I know this from the paper, if you run this use case with these with this configuration, it is fully block sparse, which means again we completely skip the fine grain masking, saving that extra overhead, and this is how you can kind of approach flop proportional speedups. So I think that's pretty much all I wanted to talk about. So unless there's questions, I think I'll stop here.
Sweet. Thank you so much, Ellie. Yeah, folks, I guess I don't see any more questions in chat, but if anyone has any more questions, Ellie, like I think he hangs out on Twitter or on Discord, so please let him know. And Ellie, thank you for coming again the second time.
Yeah, of course. Happy to. Thank you.
Cool. See you around soon. Bye-bye.